So we looked at AI, and for some reason you picked quantum computing. So I want to explain quantum computing like in an hour or something, which is a tall task, but let's try it anyway. That's me. Whatever. So I'm going to take a little shortcut. Sometimes the things I explain, it's not entirely how it works, but if we really want to go into how it works, then we'll be here for a couple of weeks. So let's not do that. Minds will be blown. So first off, classical computers, we know how they work. Like we all have one. Binaries, it's bits, just 0 and 1, and they do amazing stuff. And basically, this whole AI thing we just saw, only ones and zeros, easy. But, and what do you do with these ones and zeros? Well, we put them in logic gates, and they flip. Like 1 becomes 0, 0 becomes 1. That's the only thing your computer is constantly doing, like the entire time. Turning ones into zeros and zeros into ones. Quantum computing is different. In a quantum computer, the end result is still a 0 and a 1, but the process in between, magic. So first, why do we need these quantum computers? Well, quantum computers can do stuff we normally can't do. So one famous example, always brought up, prime factorization. Like this calculation, easy. But the other way around, given this number, what two prime numbers make up this number, that's a hard problem. Like we don't really have an efficient way of doing this. And it's a good thing that we don't have an efficient way to doing this, because if we did have an efficient way to do this, you won't be able to do online banking safely, for example, because all the encryption that we're doing is based on this problem. There are certain problems in computing which are easy, like, I don't know, sorting a list. That's easy, we know how to do that. We have efficient algorithms to do that. There are some problems that are NP hard. And for example, prime factorization, that's a hard problem. Look, it's over there. But there's also quantum easy. And this is actually bigger. Like there are things you can do with a quantum computer efficiently, easy, that you couldn't do on a normal computer. And prime factorization is probably one of them. We don't know for certain, but up to now, it is. Maybe someone comes up with an efficient way to do that, but it probably is impossible. So this quantum mechanical phenomenon, it's weird, right? It's a small scale, you cannot see it. But turns out, what is actually happening? Like this is water. Like we know water, you can put your hand in it, you get wet. If you break it up, you look really closely, what is it? It's actually hydrogen and oxygen, H2O. And you can zoom in, and you can actually see that it has electrons and 8 protons and 8 neurons. If you zoom in further into this proton, you can see it has up quarks and down quarks. And that's where our understanding stops. Like on these particles are the most basic building blocks that we have at the moment. So you have up quarks, down quarks, charm quarks, strange quarks, top quarks, and bottom quarks. And you have these electrons, muons, taus, a lot of cool stuff. Magic. So this is the world of quantum and the quantum effects. One famous example of quantum effects is obviously the double slit experiment. I'm pretty sure everybody knows about the double slit experiment. If you shoot, for example, electrons to between two small slits, you end up with this pattern. That's what you expect, but that's not what happens. You actually get this. There's an interference. Even though it's a single electron going through one of these two gates, some reason it still interferes with each other and you get this expected output. Until you measure, okay, let's see through which slot it actually came, and then suddenly you see this again. It's really weird, but that's how the world works. So these effects are weird and hard to understand. How can we use this in computing? Well, who has Polaroid glasses? Yeah, I do. I don't have the demo with me, but I could actually, there's like a small video in there. So Polaroid, what does Polaroid do? Like it messes with the polarization. So that means that there's something happening with the light. If you take sunlight, for example, or any light from a heat source, flame or a light bulb, for example, it's going in a wave. And it can go like this, or any direction, basically. And if you have this filter, something weird happens. So this filter, if light is going like this, it can go, it will get blocked because it's going like this. If it's going like this, it can just go through. And if it's going at an angle, 50% makes it through, 50% doesn't make it through. That's how this filter works. This is just what your polarizing glasses do. That's why all the glare disappears, because if something reflects off of a surface, then it's being polarized in this direction. And if you filter those out, you don't have any glares and reflections. That's a good thing. So this is just a small polarizing filter, and I'm using some Lego. And you can see it's darker in the filter because some light gets filtered out. After this light, and now I'm going to say to you, this light will change once it passes a filter. This is a weird thing. You would think light that's going at an angle, some of it just makes it through and it's still like this. No, if it comes through, it becomes completely, it shifts. So it's now completely vertical. So let's add a second filter and we turn it 90 degrees. So now only light that goes in this direction goes through, and light that goes in this direction is blocked. And you can actually see that this is true, because when I turn the filter, all light is blocked. No light comes through, because after the first filter, it changes light. So the light is now going like this, and the second filter blocks the light. Now the question is, yes? No? The question is, what if we add a third filter? So we have a third filter. So yeah, like you see, after the first one, all the light is going like this. And if you have this filter, all the light gets blocked. That's why you see nothing. And if you add the third filter in the middle, and you rotate it a little bit, it's really weird. Like normally when you have filters, you put something, and then you put something else, and then everything's blocked, right? If you have a third filter, you put it in the middle, you can shift the light a little bit and shift the light a little bit. Like, this is what happened. If you put it in front or behind, no light gets through, but if you put it in the middle, suddenly light goes through again, which by adding more filters, you can get more light coming through. And it's actually mind blown alert. And that is because after the first filter, we've shifted all the light to like, we've blocked half of it, and half of it is now completely polarized. Then we turn it to the second filter, we lose a little bit of light, and the third filter, we still get a little bit of light through. Which is weird. That's not how filters are supposed to work. You block stuff, and you put more filters, you block more stuff. It doesn't add light. This is a simple example. Normally I have these filters with me. They're very small. Usually keep them in the bag, but I don't have them with me. So, what is inside a quantum computer? Could be polarizing light. There are quantum computers that work on light polarization. There are also quantum computers that are made from electronic spin. Electrons have like a weird spinning effect. Doesn't really spin, but that's what we call it. You can do quantum measurements on them. The spin of a nucleus, same thing. There's an electrical circuit which also happens to be like with quantum effects, a Josephson junction. The cool thing is, first you need to cool it down to absolute zero, and then you can like freeze everything, and then you can have like an integrated circuit, which is, we have a lot of experience in integrated circuits, so that's a very promising technique. You've got quantum dots, which sound amazing. but it's just a particle which is bigger than an atom, which still behaves like in a weird quantum way. These are actually used in TVs. You can have a quantum dot TV instead of an LCD TV. It's just these weird effects can produce colors, and yeah, so that's cool. I don't have it. But like I said, we know how to build a quantum computer. It's just the implementation that is a bit, because at the moment there's some heat in the system, things change. And you don't want things to change when you are measuring minute quantum effects. So that's why all these quantum computers, they look like this, they look like fancy chandeliers. That's basically to isolate it completely and to be able to freeze it down. Normally there's like a big chamber put, they have this big cooling chamber, they put it up here, screw it in, and then they cool it down to absolute zero, and then you can do these calculations. But there's always leakage. Like, we want to be interacting with this system, and every action you do introduces heat into the system and makes it a little bit less cohesive. And then after a couple of calculations, these qubits just disintegrate. You cannot use them anymore. So let's build one. Normally, I have a big skippy ball that I bring on stage. Let's see if we can have something else. I'm just going to use my bag. This is also kind of round, and it has this cool Java logo on it. So let's say this is a qubit. And the state of a qubit is really weird. Like, normally you have a 0 and a 1 and that's it. So a qubit, if it's in this position, then we say it's in the 0 position. And if we measure this qubit, it will say 0. If it's in this position, with the thing pointing down, then we say this qubit is in a 1 position. If we measure this thing, it's a 1. The state of a qubit, doesn't matter how it's turned, it's always a combination between being 0 and being 1. And this state is, mathematically, you can say that it has equal probability, so it can be 100% 0, 100% 1, or anywhere in between. That's the magic part. So, yeah, mathematically, there's some state. In Java, we can just write two complex numbers. There's a probability of it being 1, and there's a probability of it being 0. Using Java, just two complex numbers. Einstein famously said he God does not play dice with the universe because he didn't believe in quantum computing. He didn't believe in quantum effects. This whole quantum realm, he thought there should be a different answer. This cannot be correct. He was wrong, actually. And we can prove that he was wrong, but later on that. So, given this qubit, how do we perform a measurement in this system? Turns out it's actually random. If you're building a quantum simulator, you have this system, and if you do a measurement, you go over all the states and you just pick a random number. In this case, if you run this code, you always get a 0 because we initialize the system with it being 0. Because there's a chance of 100% that it returns 0. So our computer, our MacBook, the Beamer, it uses logic gates to change zeros into ones. We have the same thing in quantum computing. But the gates look like this. They're actually mathematical matrix operations. That's the only thing that's being done, matrix operations. So this is Pauli. Hi Pauli. He's very famous because he came up with not 1 but 3 gates. There's the Pauli X gate, the Pauli Y gate, and the Pauli Z gate. They all do kind of the same thing. So, given our qubit, if you say the Pauli X gate, the X direction is this. So what the operation does is that it applies this rotation to it. So if it's a 0 and we do the Pauli X gate, what do we end up with? A 1. So the Pauli X gate is the same as a NOT gate. It just turns the entire thing around. Okay, so we also have this direction. What happens if we apply the Pauli Y gate? we wrote it this way, it's still a NOT. We do a different rotation, but the end result in this case is the same. We also have the Z gate, which does something else. What happens if you do the Z gate? It's this. And if we apply it again, you get back here. So if it's a 0 and you apply the Z gate, it's still a 0 every time you measure. And if you apply it again, it's still a 0. So that's a bit weird, but it sounds like this is a useless gate, but it's actually not. Because there's a difference between now you can see our logo, now you can't. So there's more state than just being a 1 and a 0. There's more encoded into this system than just our logo. So how can we test this? So in Java, again, we have this qubit. We initialize it as a 0. Then we have this matrix operation, which is just a matrix operation. We plug in the numbers of this X gate. We multiply our qubit with this matrix operation. And now we always get a 1 because we flip the state. Perfect. We're halfway there. We already implemented 3 different gates here. One thing to notice that everything you do on a quantum computer is unitary. What does this mean? Well, it basically means if you apply a gate, so for example the Y gate, and you apply it again, you get back to the state you started with. So this entire thing is reversible. Everything you do in a quantum computer up to a measurement is completely reversible, which is fun coincidence. I've actually, this together with ChatGPT led me down a rabbit hole. There's a whole field of reversible computing, which is very energy efficient computing, because if you don't lose any entropy or any bits, then you can have computers that don't emit heat, which is really interesting. Like there are whole fields of research doing this, which I had never heard of, but it was ChatGPT who taught me about reversible computing, and now I really like the fact, especially because I know that quantum computers also work that way. Okay, Hadamard is a real badass. He came up with this gate, which is amazing. Like all other gates, if you have just a single qubit, you can envision this as our Skippy ball or bag. So we already had like this gate, and this gate, but Hadamard came up with this gate. So what happens if you rotate around this, this orientation? You get this. So what is it now? Is it a 0 or 1? It's both, right? It's somewhere in the middle. And if you apply that same rotation again, you'll get back to where you start from. So it doesn't matter even if you're here, if you apply it, then it goes to here. If you apply it again, then it goes back here. So like the other gate, it has the same properties. You can apply it again, and you go back to the same state. But this leaves the entire state in a bit of a weird situation. So if we have this, this 0 bit and this 1 bit, and we do this weird gate, then you have like 50-50 chance of measuring a 0 and 50-50 chance of measuring 1. We've created a superposition. Our qubit is in a position of being a 0 and a 1 at the same time. This is also where the famous Schrödinger cat comes from. You put a live cat in a box with a small, radiation tube that might break or it might not break. And if it breaks, it kills the cat. You don't know what happened. What is the cat? Is it alive or is it dead? We don't know until we open the box. That's the famous thing. Yeah. So up to now we've seen some examples on a single qubit where you can like rotate it around and we can understand this. But a quantum computer is made up of more gates. So for example, the C0 gate is usually there's like a matrix operation which you can do. There's also like this line diagram. This is the first qubit and this is the second qubit. This means they're initialized at 0. And these notations are, this is the NOT gate, and this is the control gate. So it looks at this gate, and then it says, well, if it turns out to be a 1, then it does the NOT. And if it turns out to be a 0, then it does nothing. That goes through. So this flips the bit if the first bit is measured as a 1. So it's a bit weird because you're changing the future outcomes based on things that are not happening yet. So you can't just follow through. But once you measure it, let's look at an example. Oh, one thing to notice, this is the controlled NOT, and you can actually see the X gate in the bottom. Like that's the Pauli X gate, the NOT gate. It's hidden in the matrix operation. Actually, when you look at these matrices, it's actually incredibly simple to build a quantum computer simulator. Like there's nothing stopping you from doing that like in one evening. I've did that. So, okay. Now we're gonna do something that actually was used to convince. Well, Einstein was already dead, but to disprove Einstein and actually prove quantum computing, and that's the Bell state. So we've got this first qubit, and we do the Hadamard operation, so it becomes like this, which is 50-50, 0, 1. And then we say we have this controlled NOT, and then we have the second bit. So that means that if the first bit is 50-50, if it becomes a 1, the other one will do the NOT operation, and it will also do a 1. If it is measured as a 0, the other one won't be flipped, so it will stay 0. So these qubits are now always the same. It's either 1, 1 or 0, 0, but never 1, 0 or 0, 1, because that's an impossible state. And if we have this quantum system, we do 4 qubits, we do the Hadamard gate, and we do the C0 gate, just these matrix operations that we just saw, and you run it, you get this result. I've run it, 1,000 times, and you can see it's always 0, 0 or 1, 1, nothing in between. This is just encoded in these complex numbers, which is pretty cool. But Einstein, like I said, he didn't believe this. He was like, das ist das. Well, you say it. Your German is better. So, how can you prove that these effects are actually happening? How can you say, well, this is not a low, maybe there's some hidden information in these bits and then it ends up anyway. But there's a way to prove this, and this is the Bell test. This might be a bit hard to understand, but suppose you have 2 particles. So out of nothing, we create 2 particles. This is actually something we can do. And these particles, these have electric spin. And if you create 2 particles, they always get created in a pair, and the spin is always exactly opposite. So 2 particles, opposite spin, they get created. And now we send them into random detectors in 3 different random directions. Doesn't make any sense, but it will. So if we measure both of these particles in this direction, they will always disagree, because these are particles created with opposite spin. There's no reason that they will both be up or both be down. They will always disagree. So either it's pointing like this or it's pointing like this. That's how these particles work, because they have completely opposite spin. They're so even if we measure in this direction, one will say that way, one will say that way. They will disagree with each other. So what happens if we measure these angles randomly? And this is a very weird experiment, and I'm completely surprised that this even exists. So what if there's some predetermined plan? Like Einstein envisioned, there's probably some plan that they follow. So here's a random plan. If we measure it like this, it will say up. If we measure like this, it will say that way. And if we measure like this, it will say that way. So the first particle does these things. So the first particle agrees with 1, disagrees with 2, and agrees with 3. That means that the other particle does the complete opposite. Like for every plan we have, there's something A can do, and there's the opposite B can do. So given this plan, these are all the combinations that you could have between 1 and 2. So if we measure both in this direction, they will disagree with each other. Because we're measuring the same angle, we know these disagree. If we measure these two, in this case, they agree with each other. And we can just continue this entire thing. And for a given plan, you will see, for any given plan, that in 55.6% they will, or in this case, yeah, so they will, in 55.6% they will agree with each other. And that is for every random plan you can make. So, oh, and there are also two cases. If you have the case where they always have the same, then they will disagree 100%. But in the best option, they will have like 55.6% of the time they agree. So there are 8 possible plans, and if you add them all together, like you have to have 55.6% or higher. However, if this is based on quantum principles, and we measure the first bit, the first electric spin thing like this, the other will entirely become down. That's how quantum state works. We've collapsed the state, we know this one was up, so the other one is completely down. And if we now do a measurement, if we measure in this direction, it will always 100% disagree. We know that happens. And the other two have these chances. So in total, it's a 50-50 chance. And does this make sense? So if the state collapses and it completely disagrees and you measure then, it is 50-50. If there is a predetermined plan, there should be a 55% or higher chance of them agreeing. And if you do the actual experiments, which they've done a lot, they always end up with a 50-50 split. So measuring randomly, if there was some predetermined plan, some particle, something, it should be higher than 50%. They should agree more than 50%, but it doesn't. So this actually proved that these quantum effects are real. The moment you measure them, you change these particles. Even if you send one particle to Mars and one on Earth, and you measure it on Earth, you change the outcome of the thing that's happening on Mars. And there's no mathematically proven, there's no way that there's some hidden information that we send along, because all of these plans don't work. Like, we've proven this. This is real, which is pretty cool. So now this all remains. We've got these weird qubits. We can do matrix operations in a simulator. Wait, let's see. I literally wrote a simulator. Do I have it here? I hope I have it. Like this simulator, Schrödinger's cat. I can calculate these quantum effects. Yay, he survives, and I can do it again. He survives again. Oh, it's his lucky day. Oh, he did make it. So these quantum effects are easy to calculate. There's one problem, and that's the exponential state. If you have one qubit, it's very easy. It's just 2 complex numbers. If you have 2 qubits, then it's still easy. It's just 4 complex numbers. And if you have 3 qubits, the state is, you can kind of see the pattern here. Then it's 4 qubits. Then it's 4 complex numbers. Then it's 8 complex numbers. Then it's 16 complex numbers. And in 10, 20, 30 qubits, if you want to simulate this, you've got like a million by a million array of complex numbers that you're multiplying with matrices that are also a million by a million. And this quickly becomes too computationally expensive to actually do. This grows very rapidly. We will never be able to simulate 100 qubits, because that's 2 to the 100 states of complex numbers we need to multiply together, which is something we cannot do. So that's fun and all. We're changing this bag, we're rotating it around, and we're measuring where this Duke is pointing. How can we actually use this in a computer? How can we as programmers program something on a quantum computer? So I'm going to explain 2 different algorithms. The first one is Grover's algorithm. It has nothing to do with Grover itself. It's just some dude. And in this case, we have unordered data. So we've got, for example, a shuffled deck of cards. So it's not ordered. If you want to find data in ordered list, we know how to do that. We can do like a binary search. We start in the middle. Is it higher? No, then. So we have efficient algorithms for doing that. We don't have any efficient algorithm for random data. If I give you 1,000 books and I say it's randomly ordered, find book X. You need to start at the beginning, to the next one, to the next one, to the next one, until you find it. So that's an ON way. So for example, if I give you, I want the ace of diamonds, then you need to go one by one, until you find the card that you're looking for. On a quantum computer, we can do something cool. We can say every card has an equal probability. That's something we can do. And all the operations we do, they need to be reversible. So there's something called an oracle function. And this oracle function, no, it's nothing to do with Oracle. This oracle function is really weird. It says 0 for all cards except the one that we want. It returns a 1. This is something you can encode in a quantum computer. And then it can flip the state of the one we want. So even in an unordered set, we can say, apply the oracle function. And it doesn't change the probability. If you measure that, the probability is still the same for the entire system, but it's like rotating the deck. Like the probability of being 1 is the same, but you can no longer see it. Like this operation we can do very efficiently on a quantum computer in a single go. But that's still useless because the probability of measuring, if you do a measurement now, everything collapses and one of these will become 1, but it's still random. So what we do is we take the average probability and we rotate every probability around this average. And if we do that, so this is the average of all, and we rotate it around that average. This operation is reversible. If I again rotate around the probability of the average, we go back to like this time. But we can also apply it again, and again, and again, and again. And if you do this 50 times or 100 times, and now the probability of measuring the correct output is very high. So just by doing reversible operations, we've amplified the result, and if we now do a measurement, it will collapse and it will show 7. So this is very weird. So in unordered data, we can find the thing we're looking for in like much better than ON times. This is the square root of n, which is pretty cool. But the most famous one, and probably also the scariest one, I know governments are already collecting like all the data we send on the internet, even if it's encrypted, and they have no idea how to decrypt it. They just store it somewhere because maybe in 5 years we'll have a quantum computer. And at that point we can do this stuff. Then we can read everything you said the last 10 years. So that's still scary. So even if things are encoded now, maybe it's no longer encoded in a couple of years. And that's all because of this. The prime factorization thing I started with, this is something we can do. Like the best way we have is just trying if we can divide it by 2. No, maybe 3. No, maybe 5. So Shor's algorithm is different. So how does it work? First, we pick a random, always this random stuff. We pick a random number that is smaller than the number we are trying to factor. And then we check if it's a factor. Because if it's a factor, we are extremely lucky and we're done. It's always a good first step. So in our biggest example, the sum is 15. Our random number that we picked, purely random, is 7. 7 is not a factor of 15, so sadly we have to continue to step 2. Now we need to find the period for A mod n. What do we mean? Well, 7 mod 15 is 7. And now we do 7 times 7 mod 15 is 4. 7 times 7 times 7, etc., etc., etc. You'll start to notice a pattern. And this is true for every combination of random numbers. There's always going to be a repeating pattern. In this case, our period of repeating is 4. And this period will always be smaller than 15. The maximum that you could possibly have is 15, but it's always smaller than that. For every combination, there's some period. We need to find this period, because if we have this period, 4, we need to do one simple check. If r is odd, or if this calculation is 0, then we need to start again. Our random pick was not the best one. We need to start again. But if it's not, we can just calculate the 2 prime factors. It's a simple calculation now. And if we actually do this, we'll get 3 and 5, which is the prime factorization that we want, because 3 times 5 is 15. So, if you want to break NSA, you want to be very famous, you just have to pick a number, find its period, check this period, and calculate the 2 prime numbers. And the whole problem here is this finding the period. Because, like I said, if you are unlucky, this could be as high as the number you were trying to factor. And that's the whole reason why we have the security. It's a hard problem. This is the same problem as dividing by every number, because you need to check every number, which is not what we want. But on quantum computers, we can do something that's called a quantum Fourier transformation, and it basically solves this problem for us. So we have some qubits, and we number them, and we entangle them by applying the Hadamard operation. So we do 50-50 between all the numbers. Now, using one simple calculation, because all these numbers are equal probability, we can, in one operation, apply this period finding mechanism to all the numbers. Because we don't need the specific outputs, we just want to encode this. That's easy. The thing is, if we do this, they will all have some random probability. And if we measure, we get 7. That's not what we want. We want to find the period. So we need to transform from a signal domain, from a time domain to a frequency domain. So imagine these are the numbers we end up with. There's obviously a period in here. It repeats. If you've ever used the Fourier transformation, you will know that if you have a signal like this and you apply the Fourier transformation, you get a pattern like this with 4 distinct peaks. If the period obviously is 4. And if there are different signals in there, the period might be something else. And what we do now is that we take a measurement. So some have a very high probability, some have a low probability. So let's say we measure this, 65. And we use the scale from 0 to 128 here, and we get this 65. Says nothing. Get a second number, still says nothing. But if we continue a couple of times, we also measure 0 very often. So you need to repeat it 10 times or maybe 15 times. But then you start to see a pattern. All the numbers you have, if you calculate the continued fractions of this, it will turn out they are all a fraction of 4. That means that after just a couple of measurements, we can say that the probable period of this thing is 4. And if you know that, you can plug it into the formula, you can check if it actually has the 2 primes and it makes the right number. And basically, this is something you can do on a quantum computer almost instantly. So you don't need to check every number, you encode the problem, then you apply measurements, and you get semi-random looking numbers. But for some reason, if you do that a couple of times, you add them up, you get the correct answer. And this is a very weird way of thinking of quantum computers and quantum algorithms. But basically, that is what they're doing. And how fast is this really? If you use the best mathematical way classically to find the 2 prime numbers, you need to do it using the general number field sieve. If you use Shor's, and it's the O expression of that, and this is the O expression of Shor's algorithm. And what I found funny is that I found this answer on Stack Overflow, where some person says this is probably the speed of this algorithm. Turns out the guy who wrote this was actually Peter Shor himself. So he invented the algorithm and he was replying on Stack Overflow. I really like the dude. Yeah, but we don't know the exact boundary, but the papers say that it's 72 times log n, which is way faster than normal. Yeah, you can see here, general numbers field sieve grows exponentially, and Shor's algorithm, based on some quantum computers, like these don't exist. If they did exist in these sizes, it would scale linearly. So that's cool. Luckily, there's a solution. Right now, all of the security we're doing is based on prime numbers, but there are some algorithmic things that are quantum safe. And I'm really advocating, if you have something to do with security, make sure your algorithms are already quantum safe. Because, like I said, NSA is already just recording everything, because once they have a quantum computer, they can just decode it anyway. And maybe they'll come after you then. So there's lattice-based security, where you can have a 2D lattice of points, and you calculate a path by moving some arrows around, and then you can send these lattice pointers away, and your task is to find the original lattice used and reconstruct the path, which is, I could explain it, but it would take like another hour. There's also something called multivariate equations, which I absolutely don't know anything about. Hashes, you can encrypt things based on hashes, which is pretty quantum safe, or codes. And there's something called a supersingular elliptic curve. This is probably one you have heard about, because elliptic curve cryptography has been really on the rise, and NSA is now also advocating using elliptic curves, but there are also some elliptic curves that they pushed, which we now know that have some other vulnerabilities in them, so they could decode it. So don't really trust anything the NSA recommends, but moving to elliptic curve is probably a good idea. So if you are picking a security solution, look at elliptic curves, maybe not the one the NSA recommends. If you want to learn more about quantum computing, IBM, they do amazing stuff. They have Qiskit is their programming environment. You can, using these icons I used, where you have lines and you can connect these lines together. This is the way you can build a quantum computer using Qiskit. You can run it on a simulator, or you can run it on an actual quantum computer, which they have available in the cloud. You're just free to use. They're very small, like 10 qubits or something, but still, you can just go online and play with this. This is things you can do. There's an online simulator which I used daily when I was building my simulator, just to check if it actually works, and you can just mess with these things online. And there's Scott Arison. He has a blog about this, and he actually I reached out to him, and he replied to me, and he explained some things which I found really cool. So should definitely, and my code is online there, but it's crap. So, are there any questions?